Hi everyone, in this video we are going to look at, probably for the first time, cycloalkanes. And for instance, this model up here is cyclohexane with a red atom and a blue atom substituent. We should have enough time to get to cyclohexanes, but we are going to start with the smallest ring, cyclopropane, because these rings have associated strains with them, or stress, that add to their instability. And we're going to look at some of these stresses or some of these strains by reviewing torsional and steric, which we've seen before in Newman projections. And the third type of strain, angle strain, we'll look at for these cyclic molecules. Okay. I want us to still use our models. So two models that I want you to make, butane and cyclohexane. Those models will be useful for this video. Go ahead and pause and unpause when you're done making these two models. Okay, for cyclobutane, what I want to do is I want to go over the two strains that we saw previously, and we're going to draw Newman projections again. Situate your person. I'm going to look down the 2,3 bond, and I think the two Newman projections that I want to draw are the least stable and the most stable. And you can test yourself by drawing the least stable and most stable and comparing it to my answers if you want to pause the video. So the least stable is going to automatically be a eclipsed conformation. And I'm going to draw my front carbon like this. Okay, and here we have a methyl group. Okay, so the front carbon is right there. It has a methyl group and two hydrogens. If I want the least stable, I want the methyl group in the back to be right underneath the methyl group in the front. So I'm drawing the eclipse conformation. Hopefully this is now reviewed for most of you. And why is this the least stable? Because there are two types of strains. The first type is called torsional, and some people know this as eclipsed strain. And we are going to see torsional strain in our cycloalkanes. Just be patient. And the other strain is steric strain, bumping strain. Is that true? If I have a model of butane, hopefully you have that model too. This is fully extended, so this is actually fairly stable. But the unstable conformation is when you have the two methyl groups eclipsed. And let me tilt this so it looks like my drawing. You see how the two methyl groups are eclipsed? And torsional strain is the repulsion of bonds that are kind of close together due to electron repulsion. But the steric strain is these two methyl groups getting close enough so that hydrogens are now bumping each other. Okay? So again, this is eclipsed right there. What about the most stable? Compare your answer to mine. Most stable, we're going to automatically draw a staggered conformation. I'm going to keep the front carbon the same as here, but now I am going to put the methyl group down here in the back. Okay. This is called staggered anti, okay, because there is a staggered gauche conformation. Thought I heard knocking. So here there's no steric strain and there's no torsional strain. Okay. But I did want to review. Let me review one other conformation. So we have torsional, we have steric. What's the other staggered? The staggered gauche. Staggered gauche is interesting because it's staggered, so it's fairly stable. But the two methyl groups in this case are going to be close together, closer at least compared to anti. And that's where we get steric strain. So this one has no torsional strain, but these are close enough where you could start to feel the hydrogens feel each other, and they start bumping into each other. So we do have steric strain. No torsional strain. Okay. But there's a third type of strain, angle strain. We don't have any angle strain in any of these because these carbons are fairly tetrahedral. The bond angles are all 109.5 degrees. Okay? But if I take a look at cyclopropane, I didn't ask you to make a model of this because I'm afraid your models might break. Because if we take 3 carbons, look how strained this is. I got to connect these 2 carbons on the bottom. Okay, so I'm going to have to kind of bend. Oops. Look at that strain. Look at the bending, right? These are, I guess these will be considered convex. So my bonds are strained right here. Why? It's because of angle strain. If I think about this triangle here, cyclopropane, this internal angle is, oops, my geometry. This internal angle is 60 degrees. Okay, but it's still a tetrahedral carbon. It's still sp3. Isn't the bond angle for sp3 and sp3 carbon equal to 109.5 degrees? There is a big discrepancy. There's a deviation. So this deviates far from ideal. It's still possible. Cyclopropane does exist, but the overlap of the orbitals making the bonds is not very aligned, and you actually see a bending, okay, when you look at the orbitals connecting these 2 atoms. Do you remember what orbitals those are? Those orbitals are sp3. Okay, I'm not going to draw that for you, but what I do want to impress upon you is this is the third type of strain, and it is angle strain. We can't avoid it with cyclopropane. Okay, we can't avoid it. But also, and this may not be apparent to you at first, if I put in the hydrogens, let me put in hydrogens for 2 of the carbons. Okay, there's your 4 hydrogens for 2 of the carbons. Let me just put all the hydrogens. Okay. Alright, this is the full molecule for cyclopropane. Okay. Look at this. I'm going to look down one of the carbon-carbon bonds. So you're allowed, and it's possible to draw a Newman projection because all you need is a front carbon and a back carbon. When I do that, what do you notice about the hydrogens? Do you see how the hydrogens in the back are being eclipsed by the hydrogens in the front? Okay. It's eclipsed. And there's actually no way to avoid having the hydrogen bonds eclipsing each other when you have a cyclopropane. So you have much, let me emphasize that, you have much angle strain and much torsional strain. You know, a torsional strain, we could think of it as eclipse strain. It's the repulsion of these bonds, the ones that I'm pointing at, the 2 pink bonds right there. Okay, I know they seem kind of far, but they're not as far as if these were staggered. Okay, the eclipse distance is closer than the staggered distance between these two carbon-hydrogen bonds. Much angle, much torsional for cyclopropane. Let me relieve the strain. Look how this molecule pops open by just a little bit of activation energy. Okay, you see how it pops open, and it really wants to be 109.5 degrees, not the 60 degrees that I showed. And it looks like now my models are kind of bent out of place. Okay, cyclobutane. Square. What is that bond angle? That bond angle, internal, is 90 degrees. It's still far from tetrahedral. It's still far from 109.5 degrees. So yes, we're going to have angle strain. Not as much as cyclopropane, obviously, but it's still not great. And when I try to make that molecule, okay, it's going to be a little bit easier, but still I got to bend the bonds, bend the pieces a little bit. And you'll probably notice, if you look very carefully, that the carbon-carbon bonds are still a little bit bent. They're still convex. Okay, right there. Okay. It's kind of hard to see with the shadows. And then let me show you the side view. It's flat. Okay. Well, what about torsional strain? Do we have any torsional strain? Let's take a look down at one of the carbon-carbon bonds. And let's take a look at right there. Ooh. Okay, so those are eclipsed. But there's a way to relieve some of the torsional strain, but only some. Relieve some torsional strain by what's called puckering. I'm going to try to draw it flat, but I'll show you with the model, because drawing it flat it looks a little bit unreasonable. Okay. By making, yeah, not the best drawing. Let me try it one more time. Nope, still did not work. By raising up one of the corners, by raising up one of the corners and making a fourth atom out of the plane, you're able to get this to look a little bit more staggered. And let me try to prove that to you right now. So here's your square, cyclobutane. It's flat, okay, and we see that it's eclipsed, okay, fairly eclipsed. By taking this corner on the right and I pucker it like this, okay, I bend it up a little bit. What I'm trying to do, if you look at now down the carbon-carbon bond, you see how it's a little bit less eclipsed and starting to become more staggered? Let me see if I could even force it a little bit more. Right there. Do you see how that looks like a staggered conformation now? A staggered Newman conformation? Let me just let go. Okay, so it's still, because it's a square, it's still trying to get into the eclipse conformation, but it's a little bit better. And now when I look at it on the side, you see how it's a little bit puckered. It's not, all four carbons are not in the same plane. Let me do it this way. Okay. It still has torsional strain, but not as much because of pucker. So bottom line, you'll relieve only some. So still we have angle, and still we have torsion, okay, but less than cyclopropane. Cyclopentane. Let me make that model for us real quick. Cyclopentane, the pentagon, right? There it is. Make it flat. Cyclopentane. What is the internal bond angle for a pentagon. This one is not as intuitive. We have a bond angle here, and I looked up a formula. If you take 180 times n minus 2 divided by n, that will equal the bond angle. And this actually works for our cyclopropane and cyclobutane. It works for a triangle and it works for a square. But let's show you for the pentagon. 180. N equals the number of sides, so 5 minus 2 is 3, divided by 3. Wait, divided by 5. Woof. Okay. And this is 180 times 3, divided by 5, 108. Whole number, 108 degrees. Let me just double check for a square. For a square, it's 180, 4 minus 2 divided by 4. 180, 4 minus 2 is 2. Okay. Good, divided by 4. 90 degrees. Okay, so it works. Whoa, 108 degrees. That's really close. It's almost 109.5 degrees. So we're going to say no angle strain. Okay. And yeah, if we have this cyclopentane flat, do you see how the bonds aren't concave anymore? I keep saying that wrong. Convex anymore. Okay, they're not bowing outward. But when cyclopentane is flat, we still have what? We still have eclipsed hydrogens. Look at this. Look at the front carbon here. Eclipsed. So we are going to, again, pucker cyclopentane. And you could pucker it in many different ways, but you're puckering it to see if you could get anything that is more staggered-like. So now look at this front carbon. Right there. Do you see how that's staggered? This is the back hydrogen right here. See how it's opposite this hydrogen here? And we have staggered. Now I can make it super staggered or really staggered by just... how about that? That looks staggered right there. Look down this... look through this carbon bond right here. Okay. No angle strain. No torsional. We'll go with no torsional. 5-membered rings actually are pretty common in biology, like fructose. One of the monosaccharides used to make, well, it's a fruit sugar. Fructose is a 5-membered ring. Okay. Next. Well, the bond angle for cyclopentane is great. I think we're going to run into a problem when we go to 6 sides, because now we're making that angle more obtuse. Okay. This is the model I asked you to make, cyclohexane. So let me flatten this out, and actually take your model and try to flatten it. Try to make all of those carbons in the same plane. So to do that, I'm going to put it on my paper and I'm going to flatten it like this. I'm making sure that all 6 hydrogens that are on the bottom touch my paper. Okay. So our model right now is cyclohexane, and I'm going to specify that we're going to look at it in the flat conformation first. When it's flat, okay, it's a little bit hard to see, but look at my carbon-carbon bonds now. They are actually convex. They're bowing inward. Why are they bowing inward? Because the angle for a hexagon, the internal angle, is 120 degrees. Okay, let me just fill this in. For the pentagon, it's 108. Whoa. So for cyclohexane, we do have some angle strain when it's flat. So when it's flat, I'm not sure why I put quotes, because it is flat. Take a look at my molecule. Make sure all the 6 hydrogens are touching the page. The 6 hydrogens pointing down. And look what happens when I put it on its side. Right there. Do you see all 6 carbons are in the same plane? So we're going to call that a flat cyclohexane. When it's flat, you have angle strain. That's not great. Angle strain. And just like with all the other cycloalkanes, when they are flat and no puckering, you have eclipse bonds everywhere. Carbon-carbon, the bond here, we have eclipse carbon-hydrogen bonds. When I rotate this, there's our new carbon-carbon bond that we're looking down. It's still eclipsed. Okay. Torsional. Okay. What happens with cyclohexane? Okay. Cyclohexane actually is also another very common ring size in biology. We talked about fructose, glucose. Glucose is a 6-membered ring. Okay. Okay. What's going to happen here is you're going to take your model, and I'm going to zoom out so you can see better what I'm doing. You're going to take your model and hold it 1 carbon on each hand and have the carbons across each other. Right hand, left hand. With the right hand, you are going to, I want to do this correctly, you want to push that carbon in your right hand up. And you want to take the carbon in your left hand and push it down. Okay? And you should have something that looks like this. If your models are good and they snap into place and the angles are set, then this is actually a more stress-free conformation. Like literally in the model, the bonds now are a little bit straighter, there's no bending, and the model, at least my model, it's snapped into place. Look what happens when I lay it down on the paper. Okay. It's hard to see, but it's only touching the paper with 3 hydrogens instead of the 6 when the molecule was flat. Let's turn it on the side. This will take a little bit of practice. Now, look what I'm going to do. I know I'm holding it so right now that the 3 hydrogens, the ones down here, okay, are all going straight down. But let me tilt it a little bit. And what do I have here? It's hard, a little bit hard to see, but we have a chaise lounge. You know, imagine that you were a little person and you sit down right on this chair. Your back will be here. Your head will be right here. Okay? Your butt will be right here, sitting on this horizontal plane, and your legs come down to the left. Okay? It's going to be difficult at first. I usually tell my students to draw this chair 100 times to get practice. But let me show you in this video how I would draw the chair. So we're going to make what's called a chair conformation. Remember the title of this unit, Alkanes and their Conformations. To draw a chair conformation, at least one of them, you want to draw 2 equal length lines that are horizontal, and you want to offset them. And I'm making the bottom line offset to the right. Okay? So let me show you, let me do that again. Okay. The back of the chair. The back of a chair, you want to put a dot not directly over this end of the line, but push it off to the right a little bit. Right there. Okay? And you want to connect that dot. Okay. For the legs of the chair, okay, let me try this. Let me do this in steps. So again, two horizontal lines offset. The back of the chair, oops. Again, it takes practice, right there. And then the legs of the chair, right there. Okay. So for me, that's a good looking chair. In the textbook, they sort of tilt it a little bit. And in the textbook, they have it drawn like this. Okay. So the chair is a little bit, you're elevating your feet a little bit. And you can see that with your model. So here is the chair I drew, but the butt is horizontal. The butt is perfectly horizontal, but in textbooks they like to draw it like that. Okay, like that. So the butt is kind of raised a little bit, and you're kind of leaning back right now in the chair, almost like a, like a beach chair. Okay. Both of these are the same type of chair, though. Okay. Now the issue is, remember when I talked about making the chair from a flat cycloalkane, like this? So this is flat, and I have it like this. I told you with the right hand, raise the carbon so it becomes the back of the chair. And your left hand, push the carbon so it becomes the legs of the chair. Okay. I know it's a little bit overexposed, so you can hardly see the white bonds, but there's your chair. And you can definitely see the head part, and you can definitely see the legs part on the left. But what if I asked you to do the opposite? What if I asked you to take your right hand and make it the legs of the chair, and the left hand and make it the head of the chair? Now my head is pointing in the opposite direction. So there are actually two chairs conformations for every cyclohexane. And let me show you. Here's my stick figure. There's my head, my back, my legs, right there. So you see how that person, when they sit on this cyclohexane, they're looking to the left. How do you get the chair that looks to the right? You offset your two initial lines in the opposite direction. So now, look where my head is. I'm going to use pink, because instead of putting this carbon down, I'm going to raise it up. For me, I'm not sure why this happens, but the second chair, the one that looks to the right, I suck at drawing them. I have to really take my time, or else it's going to look really off. Not bad, okay, but it's a little bit slower than me drawing this chair. In the textbook, how would they draw this? In the textbook, they would raise the butt a little bit, but still, the feet are on the right, and the head is still on the left. Okay. For me, it doesn't matter how you draw this. It just matters that I be able to tell which direction your person is looking towards when you make the chair conformation. So here, there, looking to the right. We're not going to do this in this video, but what are we missing? We're missing all of the hydrogens. Now I know this is a line drawing, so the hydrogens are implied, but when you draw a chair conformation, you want to draw at least some of the hydrogens to show the orientation of those hydrogens. Here's a chair conformation, again, with the person looking to the right. You'll notice that some hydrogens are straight down, some hydrogens are straight up, some hydrogens are down angled, some hydrogens are up angled. In a future video, we're going to draw all 12 hydrogens for these two chair conformations. Okay, but in the meantime, practice drawing your chairs looking to the left and your chairs looking to the right.